So as a reminder, this is what you were building. This was your function generator. Resistor. What is this circuit doing? What is this transistor doing?
Making the current bigger.
It's basically creating a current source.
Yeah.
Right? So this is a current source. Right? And the value of the current is set by what? So you're right, it amplifies the current. The current through here is an amplified version of which current? Collector, base, emitter going into the base, right? The base current, right? So this is an amplified version of that, right? We'll call this IC. IC was equal to what? Do you remember? It was beta IB, right? And this beta was around 200, right? And then, so then how do we set this current? Well, if this is your Vin, right?
Where's this?
Sorry?
Resist.
Right, across the resistor. And remember, this point always sits at around 0.6 to 0.7, so let's say 0.6, right? Above ground, because this is ground, right? This is one diode, right? So this is 0.6. So Vin minus 0.6 over that RB, or Vin minus 0.6 over 680 gives you the amount of IB, the current there. Now Vn, we set the peak voltage to 1, right? 1.25, right? So then, so if I were to draw that sine wave that is coming out of the function generator, what would it look like? So I have the offset, right? I want somebody to come and draw it for me. So, first of all, it has an offset of 1.25. What does that mean? What is the offset?
So is the offset? Wait, is the offset makes it go up, right?
Exactly.
Okay. Wait, what
By
makes
that much, right?
Yeah. What makes it go like left and right? It was the
Left and right.
like never mind.
Okay. So mark the 1.25 first. There you go.
You can make it anywhere, right?
Yeah. So let's say this point is 1.25, right?
Yes.
So if you just draw this imaginary line, then your sine wave is going above it by how much? If the amplitude is 0.5, the peak to peak is 1.
So it'd be up 0.5.
Right, exactly.
Okay, so we'll just make this 1.75.
Right, there you go.
Would it start? It started like that, right?
So it's a sine wave, right? So it goes exactly between those.
Yeah.
Yeah.
Let's try.
There you go. Perfect. Yeah, that's what it looks like, right? And that's what you see on the scope, right? So then the maximum voltage that you would see is 1.75, right? So this maximum, if I look at the maximum Vn, is 1.75 minus 0.6 over 680. That gives me the amount of current that is going in, right? And then that determines how much current I'm pushing through here, right? And so to set that current limit, if I look at this, and if I say this is approximately 1 divided by 680, 1.5 milliamps. Okay? And if I multiply that by 200, then that's about 300 milliamps. Right? So I guess we can set that current limit to about 300. And then so we're putting that sine wave in, right? That's going to create the current. The current is going to be like a sine wave going through here. And remember, when we push it through this LC, right? At a particular frequency, that that sine wave is going to get amplified, or it's going to, what we call the resonant frequency, right? That's the point that you're pushing the swing at the perfect moment, right? At that particular frequency. Otherwise, you're pushing it the wrong way. So when you look at the voltage over here, it's not going to be as big, and it's not going to look as good. Okay, so that's what you're going to see on the scope. And then you're supposed to measure what that amplitude is at those different frequencies, and then by changing that frequency, find where that resonant frequency is, where the amplitude is the largest across here. Okay?
Yeah.
Okay. So if you remember, we have been talking about that any signal you can show mathematically that it's composed of a number of sinusoidal signals, okay? A sum of sinusoids, all right? We've talked about this a lot. Now, the actual math to show it is complicated beyond the scope of this class, but we can use examples to show how that works. And one of the best examples is the square wave, and that's why we keep using the square wave and try to show that there are certain frequencies in there that if it gets, that particular frequency gets tuned to the tank circuit that we're using, that's the one that is going to pop out, okay? Now, if a signal is a periodic signal, well, okay, what's the difference between periodic signal and a non-periodic signal? Give me an example of a periodic signal.
It repeats every period.
Right, so give me an example.
Sine wave.
So,
Very good.
definitely sine wave is a periodic signal. Okay, what else? What other?
Batman picture.
Sorry?
The Batman picture.
Batman picture?
Someone made a Batman wave
Oh.
from like a certain
Cosine.
Cosine. Okay, what else? What else is
Square.
periodic? A square wave, right?
ramp wave.
We have or a ramp wave, exactly. So we have a square wave that is periodic. We have a ramp that is periodic. So these guys, okay, if you were look at the sinusoids that generate these guys, right? You have discrete frequencies. Okay? So for example, for a square wave, if this square wave is a 100 hertz square wave, the frequencies, the sinusoid frequencies that are present in the square wave are 100 hertz, 300, 500, 700, and just keeps going like that. They're the odd multiples of the fundamental frequency, right? So 3 times, 5 times, 7 times, 9 times, 11 times, all the way to infinity. They're discrete, right? But there are infinite number of them in there. Okay?
What?
There are infinite number of it.
Wait. Start over.
So if I were to look at all the sine waves that add up
Oh,
to
okay.
generate the square wave, it would be a sine wave
Okay,
at 100
okay,
hertz,
okay.
300 hertz, 500, 700, keep going the odd multiples of this original one, and you just keep going. You never stop.
That's a perfect square wave.
That's a perfect square wave.
But then there's gonna be
Okay.
noise.
Yes. So,
And you can't
so that's
go
what we're going to
to-
look at. Now, but if I look at a signal that is not periodic, so for example, if I look at just a pulse that is 0 before T1, it jumps to whatever value, let's say 1 volt, and then it goes back down at T2. If I look at that, is that periodic?
No.
That's not periodic. I can still show this as sum of sinusoids, but then the frequencies that are present in this one are not discrete. So if I were to look at the spectrum, like for this one, as I said, if you look at all the frequencies for a square wave, right? If I'm looking at it in the frequency domain, right? I have 1, 100 hertz, then I will have another one at 300, then I will have another one at 500, like that. They're discrete, right? But if I were to look at this one,
It'd be good.
it's going to be continuous and it's going to look like this. So they're not discrete anymore. They're all these frequencies, all these tiny frequencies are in there. It's going to be a continuous waveform. Okay? So I was going to actually show you a couple of those examples up here. So let me do this one first. So this is another application. This is actually, you can download it for free. It's an awesome program for doing math stuff. So here I am.
Wait, what's it called?
It's called Octave.
You can see the code of it.
So this is the code that I'm doing math, right? It's coding is very simple. It's very C-based like. So here I'm going to look at the square pulse, right? I'm going to look at its spectrum, right? So I'm going to run this program and it's going to plot them.
This is all the sine waves that make up this pulse.
So see,
Oh, so you
This
use the
is-
app to plot it?
sorry,
You use the app to plot it?
yeah.
Oh,
So
okay.
so this is the pulse in time domain, right? It's 0 before it reaches this point, then it jumps up to 1, and then it comes back down and goes to 0, right? That's it. That's the signal. And this is all the frequencies. This is the way it looks like in the frequency domain, which means that it has this frequency. So all these sine waves, right, with these amplitudes are getting added together. And these are all the frequencies. You can see it's continuous and it goes on forever.
So if you added up all the amplitudes of all those frequencies together, you get that pulse.
You get that pulse back. Okay, so now let's look at a square wave.
Is radio named after anyone?
Radio, no, Mr. Radio.
Thomas Radio.
No, those radio waves. It's just, okay, so this is a square wave, and as I said, now you have these discrete frequencies. So this is a square wave at 100 hertz, and you can see there's a frequency as 100, and then 300, and then 500, and then 700, and I haven't shown the rest of it.
And so if you took a piece of paper and added these all together, you'd end up with the on right
Okay.
hand side. Right, add all those sine waves
And
together.
that is exactly what I did in this spreadsheet. So this right here, the orange one is the sum of the different sine waves. So first of all, here's the equation up here.
Wow.
Where did my cursor go again?
Well, that's a picky equation.
Well, it's not
Right
just
here.
it's just a sum, a
Right here.
summation sign.
See? And you can see the sum over there? So I'm going to write it up here.
It's just it looks complicated. It's just a sum of a bunch of sine waves.
So I can
Look at the
show
right-hand
a
side.
square wave as
Oh.
4 over pi
Okay.
sum of the magnitude goes 2i minus 1 sine of 2i minus 1 times 2 pi f naught t.
What is the knot again?
This is the fundamental frequency. So for example, for this one, I've set it to 100 hertz.
There's 100 hertz.
Do you see it
square wave.
right here? If
Yeah.
not, I set it to 100 hertz. Okay? So then, I goes from 1 to infinity. So, if I put I equal to 1, what do I get? I get, so first of all, I have 4 over pi. I put 1 in here, 2 times 1, 1, minus 1, 1. So amplitude is 1, sine of, this is again is 1, 2 pi f naught t. And you can see, this is it. This is that first frequency, that fundamental sine wave, fundamental frequency. It's scaled by 4 pi to give you the orange one. Okay?
Okay.
Then, if I is equal to 2, what do I get? 2 times 2, 4, minus 1, 3, so I'm going to get 1/3 sine of now 3 times 2 pi f naught t. And you just keep going like that. So that's what we're going to do. Here, I'm going to add that second one, which is going to give the 3 times the fundamental frequency. So if I put a 1 here, see now,
Whoa. You just added those two frequencies together.
this is the fundamental one. This is the one with the 3 times the frequency, right? When they get added, you get that.
Looks like a wisdom.
So now you start to see, oh, it's like, I can kind of see a square wave there, right? Now let's add in the next one. Okay, so now I just, this one came in, got added, and we get this.
It's getting squarer.
Yeah, right? So I'm going to just keep adding it, right?
This is the ninth.
That was the 7th,
This is ninth.
the 9th,
These are called harmonics. It's ninth harmonic.
11th harmonic, 13th. So down here, I just plotted only 11th, well, up to 11th harmonic. Because if I wanted to plot more, it would get really busy, right? But the sum is showing the sum of all the harmonics that I'm adding.
Well, what 100th harmonic would be?
So 15, oops, 17th, 19th, and then let me just add, I have it up to 25th harmonic. Let me just add all of those at once, and get that.
Wow.
You still got like a little ring on the side.
Right, right.
If we
So-
added infinite number, we'd get rid of the ring.
So that's why that would be really hard to do in on the spreadsheet. So that's why I created this one. And then you guys are going to see I've gone to the 200th harmonic. It's going to take a while. So it's going to start with the first one, second, and you can see N on top is showing the harmonic being
This
added.
is so cool. When I went to school, you couldn't see things like this. We had no computers. You had to draw this by hand.
So look at that. So
Wait.
we're at 35th harmonic.
Wait, you really had to draw this by hand?
Yeah, well, we couldn't go that far.
Actually, that's giving the I. That's giving the I. Up there, like 56, 57, but that means 100-something harmonic. And this goes all the way to I equal to 200. It's going to take you a little bit of time, but you can see now. See now, as the more harmonics are being added, the center is getting smaller and smaller. At some point, the center becomes almost flat, and then you can see the edges are also shrinking too. There's also
just looks
there's
like a square wave
the
with
Gibbs
one.
phenomenon too that I'm not going to talk about, which
I don't
causes
know.
the ringing portion.
You have to explain that.
Wait, what?
There's some other phenomena that happens that gives you more ringing on the edges, but there's a way of getting rid of it. So this, I have that in here.
This is so great for visualization. There you can see exactly what's happening.
So this is what we're saying, right? So now you can see that this square wave, right, is the sum of all these sine waves. Okay, so let me just tell you one more thing before we do this.
One more thing.
Okay, so see, we stopped at 200, right?
That's a pretty good
That's
square
a
wave.
pretty nice square wave right there, right?
Oh,
So the other thing that I wanted to show you here, so I don't know if you noticed that as we were looking at the square wave here being generated, I also was showing the different frequency components here, okay? Which is this one's showing it down to, I
Wait,
can't
is that
remember.
exponential?
No, remember it's basically it's going down as 1 over, so it's
Oh.
1/3, 1/5.
And his scale on that is not log, it's linear scale.
Yeah, so
You
it's
see it's
linear
linear
scale.
scale.
If I do a log scale, then it's going to be more gradual. Okay? So I'm hoping that gives you a little bit better understanding of when we talk about any signal can be generated as a sum of sinusoids.
Wait, anything?
This is a really good example. That's what we were saying, right? Any signal,
Any
theoretically,
A
we can-
chorus singing a tone, any signal can be
So-
generated with a bunch of sine waves.
Now, so the other important thing is, you know how we looked at that tank circuit and then you guys looked at it over many frequencies, right? And then you figured out, okay, so if I push in different frequencies into that circuit, the output is gonna look like this, right? So now, if I have a signal that I can break it into its components of frequencies, then I can come and say, all right, now what would happen if I push a square wave through this, right? Well, what is gonna happen? That's like taking those frequency components, multiplying it by this, right? Okay, so if I take that, it's gonna come and say, well, I'm gonna squish the first, actually, right here is like 1, multiplying it by 1, right? So it's gonna do this, it's gonna do this, it's gonna do this, but then it's gonna get over here. That particular frequency is gonna amplify it. Like that,
Oh.
right? And so what you're gonna see, that's when you see that ringing. Because it has taken that one particular frequency and has amplified it, and so that pops out and you see that one ringing, that one particular frequency.
Oh.
Or if I now find a circuit that goes, instead of going flat like this, if it actually went like this, then I can get rid of all the frequencies here, all the frequencies here, and then just bring out this one particular frequency. That's why it's important to look at all signals as sum of sinusoids, because then I can look and see what happens when I push it through a circuit.